Alright, problem 70. So, in this one it says that there is a 5 kilogram box. I'm lazy, so this is that's a box, okay? 5 kilograms. 5 kilograms. And it's sitting at the bottom of a ramp. It is 8 meters long. Actually, the ramp ends because it's 8 meters. So that's 8 meters. 8 meters. And then it's up against like the ground, you know, because that's how ramps work. Anyway. And then it has an angle of 30 degrees above the ground, the horizontal, the horizon. The kinetic coefficient of friction is 0.4, and the static coefficient of friction is 0.43. And then it asks us what constant force applied parallel to the surface of the ramp. So force this way, it's parallel, totally parallel. What force that way, so parallel, is going to get this box, which is totally a box and not a ball, up to the top of the ramp in a time of 6 seconds. So t equals 6 seconds. So now for this one, it gives us the coefficient of static and kinetic friction. They're very close together. With this, it also asks us to do it in exactly 6 seconds. So I'm going to just ignore static friction because they're close enough together that it's unlikely that if you get to move 8 meters in 6 seconds, that's more than a meter per second. I doubt that 0.02 is going to make a difference, and if it did, then we wouldn't be able to get it to the top in exactly 6 seconds. With the constant force, it would be less than 6 seconds, and at that point you could pick any number you want. As long as it's big enough, you'd probably be safe. So we're just going to focus on the kinetic friction, ignore the static friction, and pretend it doesn't exist because I don't want to deal with that. So the equation we're going to use is delta x equals v naught t plus 1/2 a t squared. So the ball starts at rest. The box, it's a box. The box starts at rest, so v naught is 0, which means that part is 0, plus 1/2 a, which we are trying to find, and then 6 seconds squared equals delta x, which is 8. That is a terrible 8. We'll just do it that way. That's still terrible, but it's less terrible, so we're going to go with it. So 6 squared is 36. That's 1/2 at. So 36. So we're going to multiply this, so you get 16. Got to get rid of the 1/2. Then you divide that by 36 equals your acceleration, and that comes out to be something if you do things. So that's going to be 18 over 8, I believe. Does that sound right? That sounds kind of right. Yes. Which then you can simplify this down to be 4 over 9 meters per second squared. Okay, so that's our acceleration that you need to hit. So that acceleration is going to come from the forces, or the sum of the forces. It's going to come from some forces. That's going to equal your mass, which is 5, times acceleration, which is this. But your sum of your forces is actually going to be two different things. So it's going to be your force, which I'm just going to call F because I'm lazy. So it's going to be your force that's pushing up perpendicular. We're going to label this so we don't get confused. Or so you don't get confused. I'm not going to anyway. So it's going to be this minus the force of gravity minus the force of friction. So to find exactly what this force is now, we know that this force sum is also going to equal to 4/9 times 5, which is 20 over 9 newtons, which is going to equal all of this again. So if we find these two and add them to this, we get this, and that's it. So, force of gravity is going to be something like this. So here's our box. Here's the thing it's on. So you're going to have a normal force pushing upwards like this, which doesn't really matter because we're focusing on this, which is perpendicular to that, so we can ignore the normal force actually. And I'm just going to redraw this because I just, drew stuff right through and made a mess. So you have your box, you have the ramp, you have a force that's pushing it up, you have friction, which is pulling it back, which is going to be less because we're moving it, and then you have the force of gravity, which only part of that is going to be acting in any sort of way that we actually care about. So your gravity is actually going to be something like this. You have your y component and your x component. We're worrying about the x component here. Let me draw the ground back in because it's important. So to get this one, we're going to have that dotted line there. The angle right here is going to be 30 because it's going to be the same as this, because triangles and stuff, they do things. But that's not important. So that angle is going to be that, which means that this is the force of gravity. Force of gravity overall, so we're trying to find the force of gravity in the x direction. So force of gravity overall is going to be equal to 5 kilograms times 9.8 meters per second. And then its sine, because it's opposite, so opposite of the angle is this one right here, over adjacent equals the thing. So if you multiply both things by the adjacent, you get that the force of gravity is going to be equal to, so f of gx equals 5 times 9.81 meters per second squared times the sine of the 30. So, I suppose I could do this by hand, or I could use the calculator that's right in front of me. So 5 times 9.81, that's a 0.81, times the sine of 30, that equals 24.525. And I believe that is pretty exact, so we're just going to leave it like that. So that is this guy up here. So now we need to find the force of friction. So friction equals the normal force times your coefficient of friction. Coincidentally, the normal force is going to be equal to this y part because they're equal and opposite, because it's not falling through the floor or just randomly accelerating to the sky. It's just sitting on the ramp. So we can basically do the same thing except switch the sign for a cosine. And if you do that, you get 5 times 9.81 times the cosine of 30, and that equals, so this is force of gravity in the x, force of the normal, which equals 42.479 newtons, or something like that. I think it's newtons. Okay. Boom. That times our coefficient of friction, which is 0.4. So answer times that. Oops, I'm pushing too many buttons. Let's try that again. The force of friction equals 16.99 newtons. These are all newtons, by the way. I just haven't been writing units, so they're on there now. So now at this point we have this guy and that guy. So we can do the things. So 20 divided by 9 plus 16.99 plus, what was the other one? 24.525 equals 43.737 newtons of total force. So, if you didn't follow completely there, we just got the sum of the forces is equal to the force that we're applying, which we're trying to figure out what that force is, minus the force of gravity in the x direction, so that should be gx, minus the force of friction, because again over here you have your force, then gravity, which is acting downwards here, which you can split up into its components, the y, which we're saying is this way, perpendicular to the ramp, and then the x, which is parallel to it. So the force of gravity in the x minus the force of friction, which are both going to be opposing the force that you're pushing. So to get those, we got the magnitude of gravity times the sine of 30 to get the x component, and then times the cosine of 30 to get the y component. The y component is equal to the normal force, which multiplied by the coefficient of friction up here gets us this one here. And then we have the force of gravity in the x, which we found here. So these are the important ones that we want here and here. And then we just plug them in here. So what you end up doing is you take the f, and then that's going to be equal to, let me just start over right here. So your force, if you subtract or add this to both sides, you get force that you're trying to find equals the force of gravity plus the force that's looks like a times because it's kind of sideways, plus the force of friction, and then the force of gravity is this one. Oh yeah, and then plus the sum of the forces, which we already calculated out to be 4/9 or 20/9, because this is the acceleration. So 20 over 9. And then I just plugged that in my calculator, and that's what we ended up with. So that is the force, or the sum of the forces that we are trying to get. No, that is the force we're trying to get. That's it.